Hi, I'm Coach Cowland. This is the Nature of Science number 4. This is the math that we're going to need for physics. So some of the stuff that we're going to cover math-wise for our physics course is algebra, graphing, basic measurement, error measurement, geometry, scientific notation, and significant figures. Most of this stuff you should have covered before, but if you're uncertain about it, feel free to pause the video or go over it again. So in terms of algebra, some of the key skills that we're going to need are solving algebraic equations. This is pretty straightforward. It just involves substituting in values and plugging and chugging. Substituting values into the equations is exactly that. Knowing which equation is right is another key skill. For example, you will have a number of different equations that have similar but not always the same variables. You're going to need to select the right one at the right time. Rearranging equations to solve for any variable is a key skill. This is where you take the equation and instead of solving for one variable, you flip it around to solve for any other variable in there. And this is something that we do in physics a lot. Another thing, the last thing that we're going to do algebraically is relate equations to graphical solutions. Seeing that there's an equation of a line, that there's an equation of a curve, that this relates to the area underneath the line is key because we may get information in terms of a graph, we may get information in terms of algebra, and we'll need to switch them around. As a practice, have a go at these ones. Rearrange these equations and see how you do. We'll go over them in class. Graphing. Relating an equation to a graph is linked to algebra, as we said. Calculating the slope of a straight line graph, either using the graph itself or using points from the graph, is an important skill, something that you should have covered in math already. Identifying the intercept and then looking at the graph and seeing where it goes, making predictions based on that graph. Another important skill that we use in several areas, including thermodynamics, is calculating the area beneath the graph. Simple geometry is usually used here because we don't usually do that for curved graphs. It's usually straight line graphs. Measurement. In physics, we measure a number of different variables. We measure things like length, area, volume, etc. As you can see, these are just some of the measurements that we make in physics, but there may well be others. Being able to measure carefully, accurately, repeatedly, and precisely are all important skills. Scientific notation. You've come across scientific notation before in math, and as the term says, it is a scientifically used skill. The rule of thumb that I like to use is if a value is bigger than 100 or smaller than 0.1, then use scientific notation to express it in your answer. These are scientific notation values and standard values. Have a go at switching them from scientific notation to standard or standard to scientific notation. Feel free to pause the video and come back to it. We'll go over these in class. Significant figures. Significant figures are important to know how precisely you are measuring. Any lab that we do, significant figures should be taken into account, and any problem that you calculate, you will also need to take significant figures into account and round to the appropriate number of significant figures or decimal places. So, rules for number of significant figures. Are you listening carefully? These get kind of complex. Any non-zero numbers are always significant. So from 1 to 9, if you see them, you count them as a significant value. All zeros in between the non-zeros are always significant as well. So if there is a non-zero and there's zeros in between it, they count. They all count. All zeros which are to the right of the decimal and at the end of the number are significant. The second example here is an example of that. And all zeros to the left of a written decimal point and in a number which is more than or equal to 10 are significant. Again, the second example is a good example of that. Now we will go over some examples of significant figures, and if you have any questions about it, you should bring them up in class. But have a go at these 5 examples and see how you fare. How many significant figures are there in each value? Significant figures change when there are operations that use them. When you add and subtract significant figures, you look at the number of decimal places for both values and you go with the lesser of the two. So in this example, there are 5 decimal places for the first value, 2 decimal places for the second value. Once they're added together, you end up with 2 decimal places. You truncate your answer. For multiplying and dividing, it's not the number of decimal places, but it's the number of significant figures. The number of significant figures always goes to the lower. So the first value has 3 significant figures, the second one has 2 significant figures. Multiplied together they give 516, but then we truncate the answer to 2 significant figures to give 520. Calculating the error. Systematic errors are errors that are found in measurement and they may be due to calibration. For example, your ruler is not exactly 30 centimeters. That is a systematic error and it will occur in all the measurements you make with that error. Random errors are unpredictable, non-repeatable errors. Calculating errors, something that we do in labs, and there are several ways to do it. The first one is the mean percentage error. That's the percentage of uncertainty of the value that you measured, MV, from the actual value, AV. So the mean percentage error is 100% times the absolute value of MV minus AV over AV. Another way of calculating the error is the relative error. The absolute error is the amount of error found in a measurement, and the relative error is that error relative to what the actual value was. So here we have almost the same equation. The relative error is equal to the absolute of the measured value minus the actual value over the actual value. Okay, that's the end of the presentation. Now what I need you to do is make notes on the things that we've covered, do the examples that were shown in the PowerPoint if any, write down any questions, at least 2, and be prepared for continuing this stuff. We're going to carry it on in class when I see you. Okay, goodbye.